December 1943. Willow Run, Michigan. The sound was relentless, not the thunder of aerial combat over European skies, but something more fundamental. The rhythmic percussion of industrial transformation, metal striking metal, pneumatic hammers driving rivets through aluminum alloy at precisely calibrated intervals, the hiss of welding torches fusing structural components with mathematical precision. Every 63 minutes, another B-24 Liberator emerged from the assembly line. 4 engines, wingspan wider than most city streets, 4, 5, 1, 0, 0, 0 individual components, synchronized into a single war machine, completed faster than a Thanksgiving turkey could roast. German intelligence analysts declared it statistically impossible. American factory workers called it Tuesday. This is the story of how a peacetime democracy weaponized its industrial capacity, transforming production methodology into strategic doctrine. How assembly line protocols designed for automobiles were reconfigured to manufacture air superiority. What happened at Willow Run didn't merely build bombers, it constructed the mathematical architecture of victory itself. The 7th of December 1941, the calculus of American industrial potential undergoes catastrophic recalibration. Pearl Harbor transforms theoretical production capacity into urgent operational imperative. The United States possesses vast manufacturing infrastructure, automotive plants, steel foundries, machine tool facilities. But these systems operate within peacetime parameters. Converting civilian production protocols to military specifications presents challenges of extraordinary complexity. The strategic asymmetry appears insurmountable. Germany has weaponized its industrial base since 1936. Japan's military-industrial complex has operated at wartime intensity throughout the 1,930 seconds. Britain, despite technological sophistication, bleeds production capacity under Luftwaffe bombardment. The Soviet Union, relocating entire factories eastward to escape Wehrmacht, advances, operates under conditions of existential desperation. America confronts a fundamental question. How does a nation with zero heavy bomber production in 1940 achieve air superiority against adversaries already producing aircraft at industrial scale? The answer crystallizes in a single facility, Willow Run. This is not merely another production plant, it represents a conceptual revolution in manufacturing methodology. The challenge extends beyond assembling aircraft components. The B-24 Liberator epitomizes aeronautical complexity. A 4-engine heavy bomber requiring precision engineering across multiple subsystems, hydraulic controls, electrical systems, aerodynamic surfaces, structural, load-bearing frameworks, and propulsion integration. Each aircraft demands coordination of 4, 5, 1, 0, 0, 0 individual parts, manufactured to tolerances measured in thousandths of an inch. Previous manufacturing paradigms treated aircraft as craft products assembled by specialized technicians in small batches. A single B-24 constructed through conventional methods consumed approximately 2,000,000 man-hours. At that production rate, America cannot generate sufficient air power to achieve strategic objectives. Willow Run proposes an alternative methodology: apply automotive mass production principles to aeronautical manufacturing. Transform the bomber from artisanal product to standardized industrial output. Replace skilled craftsmen with systematized processes accessible to minimally trained operators. Reconfigure assembly from stationary workstations to continuous flow production. The concept faces immediate skepticism. Military procurement specialists question whether precision aircraft assembly can survive industrialization. Aviation engineers argue that aeronautical tolerances cannot be maintained through assembly line protocols. Even Henry Ford's own engineers expressed doubts about translating automotive methodology to aircraft of this complexity. Yet, the strategic mathematics remain inescapable. Without revolutionary production capacity, Allied victory becomes statistically improbable. Willow Run emerges not as optional enhancement, but as existential necessity, a gamble that industrial democracy can outproduce totalitarian military economies through systematic optimization of manufacturing processes. The facility under construction in Michigan would prove whether American industrial philosophy could transform theoretical capacity into tactical reality. Henry Ford's industrial philosophy, refined through 3 decades of automotive manufacturing optimization, rested on a deceptively elegant premise: systematic decomposition of complex assembly into discrete, repeatable operations. The Model T production line, operational since 1913, had demonstrated how task specialization and sequential workflow could reduce automobile assembly time from 12 hours to 93 minutes. Ford's Highland Park facility achieved this through relentless standardization, interchangeable components manufactured to uniform specifications, workstation layouts optimized for minimal motion waste and gravitational material flow, eliminating manual transport inefficiencies. By 1940, Ford Motor Company commanded unparalleled expertise in high-volume precision manufacturing. Annual automotive output exceeded 1 million units. The company's River Rouge complex integrated raw material processing with final assembly. Iron ore and sand entered at one end, completed automobiles emerged at the other. This vertical integration provided complete quality control across the production chain. Yet, aircraft manufacturing operated under fundamentally different paradigms. The aviation industry treated each airframe as semi-custom fabrication. Skilled craftsmen hand-fitted components, compensating for minor dimensional variations through individual adjustment. A typical aircraft assembly facility resembled a workshop more than a factory. Stationary fuselages, surrounded by technicians performing sequential operations in place. Production rates reflected this methodology. Boeing's Seattle plant produced approximately one B-17 Flying Fortress every 3 days during 1941. The B-24 Liberator presented extraordinary manufacturing complexity. Consolidated Aircraft Corporation's original design incorporated 451,000 individual parts across multiple subsystems. The Davis wing, an innovative high-efficiency airfoil, required precise contour maintenance to achieve specified aerodynamic performance. The tricycle landing gear system demanded hydraulic components manufactured to tolerances of 0.002 inches. Electrical systems integrated 15,000 feet of wiring through airframe structures. 4. Pratt & Whitney R-1830 twin Wasp engines, each containing approximately 9,000 components, required synchronization protocols for coordinated operation. Military procurement specifications compounded these challenges. Each aircraft required inspection verification at 127 designated checkpoints. Structural load tests validated that wing spars could withstand 380,000 pounds of distributed stress. Fuel system pressure tests ensured leak-proof performance at operational altitudes exceeding 2,5000 feet. The acceptance criteria demanded zero-defect manufacturing across critical systems. Ford's April 1941 proposal to manufacture B-24 seconds through automotive production methodology encountered immediate skepticism. Army Air Forces procurement officers questioned whether assembly line workers could maintain aeronautical precision standards. Consolidated aircraft engineers argued that the B-24's complexity precluded mass production. Too many custom fittings, too many hand-adjusted assemblies, too many variables requiring experienced judgment. Internal resistance emerged within Ford's own engineering departments. Aviation specialists recognized that aircraft manufacturing demanded skills their automotive workforce lacked. Riveting aluminum aircraft skin required different techniques than automotive steel assembly. Aerodynamic surface tolerances permitted minimal deviation. A wing contour variance of 3/16 inch could degrade flight performance. The proposed production volumes appeared mathematically implausible. Ford committed to manufacturing one B-24 per hour at peak capacity, a rate 18 times faster than existing aircraft production benchmarks. Ford's response embodied his fundamental manufacturing conviction. The problem isn't the product's complexity. The problem is inadequate process systematization. He authorized preliminary engineering studies to disaggregate B-24 assembly into constituent operations, calculate cycle times for each discrete task, and identify bottleneck constraints limiting throughput. The analysis would determine whether automotive mass production principles could transcend their original industrial context, whether the assembly line refined for Model Ts and V8 sedans could manufacture air superiority itself. Construction commenced in April 1941 on agricultural land 35 miles west of Detroit. The site selection reflected strategic logistical calculations, proximity to Ford's River Rouge supplier network, access to Michigan's Central Railroad infrastructure for material transport and sufficient land area, approximately 1,700 acres, to accommodate both manufacturing facilities and an operational airfield for bomber delivery flights. Albert Kahn, architect of Ford's River Rouge complex and over 2,000 industrial facilities worldwide, engineered a structure without precedent in manufacturing history. The main assembly building would encompass 35,000,000 square feet under a single roof, 67 acres of continuous production space. For comparative context, this exceeded the Pentagon's floor area by 9,000,000 square feet. The structure measured 3,200 feet in length, surpassing the Empire State Building's height by nearly 800 feet if oriented vertically. The architectural innovation centered on clear-span steel construction, massive parallel girders, eliminating interior support columns across the assembly floor. This configuration permitted unobstructed material flow from raw component staging through final aircraft rollout. Traditional factory architecture positioned structural supports at regular intervals, creating spatial constraints that fragmented production workflows. Kahn's design liberated the assembly process from architectural limitations, allowing workflow optimization based purely on manufacturing logic rather than structural necessity. Construction velocity reflected wartime urgency. Steel framework rose at a rate of 200 tons daily. Concrete foundations consumed 2,000,000 cubic yards of material, poured continuously to maintain structural integrity across the massive footprint. At peak construction intensity, 18,000 workers operated across triple shifts, advancing the project 24 hours daily. The facility achieved partial operational status by September 1941, 5 months from groundbreaking to initial aircraft component production. The assembly methodology represented industrial choreography of unprecedented complexity. Traditional aircraft manufacturing positioned airframes at stationary workstations with workers and materials converging on fixed locations. Willow Run inverted this paradigm. The aircraft moved continuously through specialized production zones while workers remained at optimized stations. A quarter-mile-long conveyor system, the L-shaped assembly line, transported progressively completed airframes through sequential fabrication stages. This continuous flow architecture required extraordinary coordination across subsystem production. Wing assemblies manufactured in dedicated sections achieved dimensional tolerances of 0.01 inches across 40-foot spans. Precision, comparable to watchmaking, applied to structural components weighing 3,800 pounds. Fuselage sections arrived from dedicated fabrication zones with pre-installed hydraulic lines, electrical conduits, and structural reinforcements ready for integration into the main assembly sequence. The tail section production area maintained independent workflow synchronization, delivering completed assemblies to the main line at precise intervals, matching fuselage completion rates. The facility integrated vertical manufacturing infrastructure. Dedicated machine shops produced 8,500 distinct part types from raw aluminum stock, heat treatment facilities, stress-relieved components to prevent structural fatigue. Quality control laboratories performed metallurgical analysis, hydraulic pressure testing, and dimensional verification using precision measurement equipment calibrated to 0.0001-inch resolution. Logistical infrastructure scaled proportionally to manufacturing ambition. Dedicated rail sidings delivered 250 freight cars daily, carrying aluminum alloy steel fasteners, electrical components, and engine assemblies. The adjacent airfield, designated Willow Run Airport, featured a 5,000-foot runway capable of accommodating fully loaded B-24 departures. Completed bombers taxied directly from factory floor to runway, eliminating transport logistics entirely. By January 1942, the physical infrastructure stood complete. The assembly line awaited only one critical element: the human workforce that would transform architectural potential into operational reality. Workforce recruitment for Willow Run confronted a fundamental paradox. The facility required 4,200 skilled manufacturing operators within 8 months, yet conventional aircraft assembly demanded 3 to 5 years of apprenticeship training. The traditional aviation industry drew personnel from established machinist guilds, toolmaker unions, and aeronautical trade schools labor pools, already depleted by military conscription and competing defense contracts. Ford's solution necessitated reconceptualizing the relationship between operator skill and manufacturing process design. The demographic transformation proved unprecedented in American industrial history. Women constituted 40% of Willow Run's workforce by mid-1943, compared to 12% in pre-war automotive manufacturing. Many arrived with zero industrial experience: former teachers, retail clerks, agricultural workers, and homemakers. The average age skewed younger than traditional manufacturing demographics. 34% of workers were under 25 years old. Geographical diversity reflected wartime labor migration workers relocated from Appalachian agricultural communities, southern textile regions, and urban centers across 38 states. Training protocols embodied systematic skill decomposition. Rather than teaching comprehensive aircraft assembly an impossible timeline, Ford's industrial engineers identified 512 discrete operations required for B-24 production. Each operation received standardized instruction protocols. The average training duration was 18 days for basic riveting procedures, 22 days for sheet metal forming, and 31 days for hydraulic system installation. This modular training architecture permitted rapid workforce scaling while maintaining quality consistency. The pedagogical methodology emphasized procedural standardization over theoretical understanding. Rivet gun operators learned precise tool angles, pneumatic pressure settings, and rivet spacing specifications, without necessarily comprehending broader structural engineering principles. This approach proved controversial among traditional craftsmen who viewed comprehensive technical knowledge as inseparable from quality workmanship. Yet, the statistical outcomes validated Ford's methodology. Defect rates for standardized operations performed by newly trained workers averaged 2–3%, comparable to experienced aviation technicians working in conventional assembly environments. Operational logistics presented extraordinary coordination challenges. The facility operated continuous production across 3 8-hour shifts, requiring 4,000 workers present simultaneously during peak shift periods. Workforce transportation became a systemic bottleneck. Detroit's existing public transit infrastructure could not accommodate 4,200 workers, commuting to a facility 35 miles from the urban core. Ford contracted 680 dedicated buses operating on 30-minute intervals, effectively creating Michigan's largest private transportation network. Housing scarcity compounded logistical complexity. The surrounding agricultural communities, Ypsilanti and Belleville, possessed residential capacity for approximately 8,000 additional residents. Workforce demand exceeded this by 3,400 workers. Federal housing authorities constructed emergency worker dormitories. Willow Village provided 2 500 residential units, while additional temporary housing complexes accommodated 6 800 workers in communal barracks. Many workers endured multi-hour commutes, departed Detroit at 4:00 a.m. or resided in improvised housing arrangements with multiple shift workers rotating through single residential spaces. The physiological demands proved severe. Pneumatic rivet guns generated 110 decibel noise levels across assembly sections intensity, sufficient to cause permanent hearing damage after sustained exposure. Yet, ear protection remained optional until 1943, and even then, adoption remained inconsistent. The cacophony became Willow Run's defining sensory signature, a relentless industrial percussion that permeated the facility's 67 acres, vibrating through steel framework and concrete floors, creating an acoustic environment where verbal communication became impossible without shouting. Within this mechanized intensity, individual workers transformed into nodes within a vast production network, their collective labor synchronized to manufacture air superiority at industrial scale. The B-24 Liberator's technical architecture represented a convergence of aeronautical engineering complexities that defied conventional mass production methodologies. The airframe integrated 4-5-1-0-0-0 discrete components across 14 major subsystems, each requiring dimensional precision measured in thousandths of an inch. The Davis wing, a high aspect ratio design, achieving lift-to-drag ratios of 14:7:1, demanded contour accuracy within 0.032 inches across its 67-foot span to maintain specified aerodynamic efficiency. Deviation beyond these tolerances degraded cruising speed by 8 to 12 knots and reduced operational range by approximately 140 miles. Traditional aircraft manufacturing accommodated such precision through manual adjustment. Skilled technicians hand-fitted components compensating for minor dimensional variations through individual shimming, selective assembly, and custom fabrication of interface components. This methodology permitted flexibility but precluded standardization. Each aircraft emerged as a semi-unique variation, with component interchangeability limited to approximately 40% of the airframe. Ford's production engineering mandate inverted this paradigm: achieve absolute component interchangeability across 100% of the airframe through upstream manufacturing precision rather than downstream assembly. Adjustment. This required reconfiguring the entire production system around dimensional accuracy as a foundational constraint rather than an aspirational goal. The technical solution centered on statistical process control, applied at unprecedented scale. Ford's industrial engineers implemented 1547 dedicated precision jigs, fixed mechanical fixtures that positioned components at exact spatial coordinates during fabrication and assembly operations. Each jig incorporated hardened steel reference surfaces ground to tolerances of 0.0005 inches, effectively transferring measurement precision from inspection instruments to production tooling itself. Wing rib fabrication jigs, for example, positioned 43 distinct aluminum extrusions and sheet metal components simultaneously, ensuring that every rib produced at rates exceeding 200 units daily achieved identical geometry, within 0.008-inch total tolerance. This jig-based manufacturing architecture generated cascade effects across the production system. Hydraulic line routing, previously customized during installation to accommodate airframe variations, became standardized pre-bent tubing assemblies, fabricated to fixed specifications, installed without modification in 94% of applications. Electrical harness production transitioned from custom wire cutting and terminal crimping to prefabricated assemblies manufactured in dedicated sub-facilities, reducing installation time from 120 man-hours per aircraft to 31 man-hours, while simultaneously decreasing wiring defects by 67%. Material flow synchronization demanded mathematical precision comparable to the mechanical tolerances it enabled. The assembly line advanced at a continuous rate of 2.8 feet per minute, optimized through time motion studies, analyzing 512 discrete assembly operations. Component staging protocols positioned materials at workstations with temporal precision. A fuselage section, arriving 45 seconds early, created storage bottlenecks. Arrival 90 seconds late idled workers and degraded throughput. This temporal coordination required logistical infrastructure tracking 18500, distinct part numbers flowing through 127 sequential workstations with inventory buffers, calculated to accommodate statistical variation in upstream production rates while minimizing working capital immobilization. Quality validation transitioned from final inspection to in-process verification. Rather than detecting defects after assembly completion, Ford implemented 127 mandatory inspection checkpoints distributed throughout the production sequence. Each checkpoint verified specific dimensional, functional, or structural criteria before permitting work-in-progress advancement to subsequent operations. This distributed verification architecture reduced final rejection rates from 12.3% in early production to 1.7% by mid-1944, a systemic quality improvement that eliminated rework waste while accelerating throughput. March 1944. The assembly line achieves operational synchronization that transforms industrial theory into strategic reality. Production interval, 63 minutes per complete, B-24 Liberator. This temporal metric represents not merely manufacturing velocity, but a fundamental recalibration of the relationship between industrial capacity and military power projection. The statistical architecture of this achievement reveals systemic optimization across multiple interdependent variables. Prior to Willow Run's operational maturity, conventional B-24 production required approximately 2,000,000 man-hours per aircraft, equivalent to 23 workers laboring continuously for 1 year to produce a single bomber. Ford's systematized methodology reduced this to 1,860 man-hours per unit, representing a 97% efficiency gain achieved through task decomposition process, standardization, and temporal workflow synchronization. The comparative industrial mathematics illuminate strategic implications. Consolidated Aircraft's Fort Worth facility, operating under traditional manufacturing protocols, produced 1.2 B-24 seconds daily at peak capacity. Douglas Aircraft's Tulsa plant achieved 1.4 units daily through incremental process improvements. North American Aviation's Dallas facility, implementing partial assembly line techniques, reached 1.6 aircraft daily. Willow Run's 63-minute production interval generated 22.8 B-24 seconds daily, exceeding the combined output of all other B-24 production facilities. This throughput differential created cascading strategic effects across the European and Pacific theaters. By December 1944, 8th Air Force Bomber Commands operated 2074 B-24 Liberators. Simultaneously, a concentration of air power sufficient to deliver 4,148 tons of ordnance per mission across targets, distributed throughout German industrial infrastructure. The material destruction capacity of this fleet, measured in explosive tonnage deliverable per operational day, exceeded the total destructive output of all strategic bombing campaigns conducted during World War I by a factor of Sambisishi. The logistical implications proved equally transformative. Each B-24 required 2,800 gallons of aviation fuel per maximum range mission, 1,2,800 rounds of 50 caliber ammunition for defensive armament, and 8,000 pounds of ordnance payload. Sustaining 2,000 plus aircraft in operational status demanded supply chain coordination, managing 5.6 million gallons of fuel monthly 6 million ammunition rounds and 16 million pounds of explosive ordnance logistical throughput that transformed European air bases into complex industrial ecosystems, rivaling mid-sized manufacturing cities in resource consumption and operational complexity. Willow Run's human workforce experienced this achievement through sensory immediacy rather than statistical abstraction. The assembly line's rhythmic advancement, 8 feet per minute, created temporal predictability within the manufacturing chaos. Workers at Station 94, installing hydraulic actuators into wing sections, knew that every 22 minutes another incomplete wing assembly would arrive at their workstation. This temporal regularity transformed individual labor into synchronized industrial choreography, where 1,4,000 workers operated as distributed nodes within a vast production algorithm. The rollout ceremonies occurred with mechanical regularity. Every 63 minutes, a completed B-24 engines mounted, propellers installed, fuel systems, pressurized avionics, calibrated emerged from the final assembly station. Factory supervisors conducted abbreviated acceptance inspections, control surface, movement verification, landing gear retraction, testing electrical system functionality confirmation. Within 4 hours of assembly completion, test pilots taxied the aircraft to Willow Run's runway, advanced throttles to takeoff power, and departed for modification centers, where specialized equipment installations prepared the bomber for combat deployment. The production tempo achieved what strategic planners termed air dominance through arithmetic inevitability, the cold mathematical logic that quantitative superiority sustained across sufficient operational duration transforms tactical engagements into strategic certainties. The strategic calculus of industrial warfare operates through mathematical frameworks that transcend conventional military doctrine. Willow Run's production metrics, when integrated into broader Allied manufacturing ecosystems, generated quantitative asymmetries that fundamentally altered the probability matrices governing combat outcomes. Aggregate B-24 production across all American facilities totaled 18482 aircraft between 1,940 and 1,945. Willow Run's contribution, 8685 units, 47% of total B-24 output from a single integrated production facility. This concentration of manufacturing capacity within one geographic location created strategic efficiencies unavailable through distributed production networks. Quality control, standardization process, optimization, feedback loops, and workforce skill accumulation effects compounded over successive production iterations, generating continuous performance improvements that decentralized manufacturing architectures could not replicate. Comparative industrial analysis reveals the magnitude of Allied production superiority. Combined Axis aircraft manufacturing Germany, Japan, and Italy produced approximately 189,000 military aircraft across all categories, between 1,939 and 1,945. United States production during equivalent timeframes, 3,2,4,7,5,0 aircraft. This represented a 1,7,2,1 quantitative advantage before accounting for qualitative factors, operational range, payload capacity, technological sophistication, and maintenance reliability metrics, where American designs demonstrated systematic superiority. The strategic implications manifested through cumulative attrition dynamics. Luftwaffe operational doctrine emphasized qualitative superiority. Highly trained pilots operating advanced aircraft in concentrated tactical deployments. This methodology proved effective during early war engagements, when German aircraft production matched immediate replacement requirements. However, the calculus shifted catastrophically as Allied production volumes escalated beyond sustainable attrition thresholds. Consider the mathematical architecture of strategic attrition. If Luftwaffe fighter production averages 2,100 units monthly, while sustaining combat losses of 1,400 aircraft monthly, the net accumulation permits gradual force expansion. When Allied bomber production delivers 3,800 heavy bombers monthly, each requiring defensive fighter intercepts, consuming fuel, ammunition, and pilot fatigue, while simultaneously inflicting 2,400 German aircraft losses monthly. Through defensive armament and escort fighter engagements, the attrition differential becomes unsustainable. German production cannot replace losses while simultaneously expanding force strength to match escalating Allied bomber concentrations. This dynamic, termed war by arithmetic in strategic planning documents, transformed industrial capacity into a weapon system possessing autonomous strategic effects independent of tactical engagement outcomes. Even operationally unsuccessful bombing missions, those failing to destroy designated targets or sustaining heavy losses, contributed to strategic victory through resource consumption, forcing German allocation of manufacturing capacity, skilled labor, and raw materials toward defensive fighter production rather than offensive weapons systems. The logistical infrastructure supporting this industrial asymmetry represented systemic complexity, rivaling the manufacturing operations themselves. Sustaining 1,800 plus B-24 seconds in operational status required global supply networks managing 47 million gallons of aviation fuel, monthly 89,000 replacement engines across aircraft lifespans, 2.4 billion rounds of defensive ammunition, and 340 million pounds of explosive ordnance. The administrative coordination tracking component, inventories, maintenance schedules, crew assignments, and mission planning across 127 operational air bases distributed throughout England, Italy, North Africa, and the Pacific Theatre, employed 340,000 personnel in logistical support roles, a workforce exceeding the total combat aircrew population by factor of 2.8. Willow Run's assembly line became the physical manifestation of this strategic logic, a visible, tangible representation of industrial democracy's fundamental thesis that systematized production capacity sustained across sufficient temporal duration, generates inevitable strategic outcomes regardless of tactical contingencies. The statistical triumph encoded within Willow Run's production metrics obscures a parallel narrative of physiological expenditure and systemic human cost, the biological substrate upon which industrial optimization operated. The 63-minute production interval represented not merely temporal efficiency, but sustained human labor intensity, calibrated to approach and occasionally exceed physiological sustainability thresholds. Operational tempo demanded continuous exertion across 10-hour shifts, 6 days weekly, a 60-hour work week sustained across multi-year employment durations. Time motion studies, optimizing assembly operations, calculated worker movements with precision comparable to mechanical tolerances, minimized walking distances between material staging and workstation, optimized tool positioning to reduce reaching motions, standardized body postures to maximize force transfer efficiency during riveting operations. These ergonomic optimizations increased productivity by 23%, while simultaneously intensifying physiological stress through sustained repetitive motion patterns. Injury documentation reveals the corporeal arithmetic underlying production statistics. Willow Run's occupational safety records, compiled through mandatory reporting protocols instituted in 1943, documented 4,789 compensable workplace injuries during peak production year 1944. Injury categorization 2341. Cases involving lacerations from sheet metal edges and cutting tools 1087. Instances of thermal burns from welding operations and heat treatment processes 846. Crush injuries from pneumatic equipment and material handling accidents, and 515 cases of progressive musculoskeletal disorders attributable to repetitive motion stress. The acoustic environment generated cascading health consequences inadequately captured by immediate injury statistics. Continuous exposure to 110 decibel industrial noise intensity, comparable to chainsaw operation at close proximity, produced irreversible auditory damage in workers sustaining multi-year employment durations. Audiological studies conducted in 1946 on former Willow Run employees revealed hearing loss patterns consistent with sustained acoustic trauma. 67% demonstrated measurable high-frequency hearing degradation, with 23% exhibiting severe impairment, requiring assistive devices for normal conversational communication. Psychological costs manifested through less quantifiable but equally significant pathways. The assembly line's temporal regimentation, identical operations repeated at 2.8 feet per minute intervals across 3,000 consecutive cycles per shift, generated cognitive fatigue, distinct from physical exhaustion. Workers described dissociative states where consciousness bifurcated surface awareness, maintained operational rhythm, while deeper cognitive processes withdrew from immediate sensory reality. This psychological adaptation permitted sustained performance, but imposed costs visible through elevated divorce rates, substance dependency patterns, and depression metrics among long-term production workers. The moral paradox embedded within this labor system achieved expression through worker testimonies documented in wartime interviews. A riveter identified as Margaret S., age 24, articulated the conceptual dissonance. "We built instruments of death with precision that honored life. Every rivet I drove contributed to bombing campaigns that incinerated cities, yet the work felt redemptive purpose, channeled through industrial discipline toward defeating fascism." This tension creation, serving destruction, industrial labor, enabling moral victory, permeated worker consciousness. The B-24 seconds rolling off Willow Run's assembly line carried 8,000-pound ordnance payloads designed to generate explosive force sufficient to collapse reinforced concrete structures and ignite petroleum-based firestorms across urban centers. Yet the workers fabricating these weapons systems conceptualized their labor through frameworks of liberation. Each bomber represented European civilians freed from occupation, concentration camp prisoners whose survival depended on Nazi Germany's industrial collapse, Allied soldiers whose battlefield casualties would decrease proportionally to air superiority achievement. The assembly line operated as a vast moral machinery, converting human exhaustion into strategic deliverance, transforming physiological expenditure into the mathematics of liberation. The 14th of August, 1945. Japan's surrender announcement initiates cascading termination protocols across American military-industrial infrastructure. Within 48 hours, the War Department cancels 17000, pending B-24 procurement orders. A procurement volume representing $890 million in contracted production value and 14.2 months of sustained manufacturing operations at peak capacity. Willow Run receives official production cessation directives on August 18, mandating immediate termination of assembly operations and workforce demobilization. The velocity of industrial deactivation revealed the fragility underlying apparent permanence. Production systems optimized for maximum throughput possessed minimal adaptability for operational downscaling. The assembly line functioned as an integrated organism. Removing individual components disrupted entire systemic equilibriums. Reducing production from 22.8 aircraft daily to 0 required complete shutdown rather than graduated decline. Workforce demobilization proceeded through systematic phases, governed by seniority protocols and federal re-employment mandates. Initial separation notices affected 12400 workers within the first week personnel, classified as temporary wartime hires without contractual continuation guarantees. Secondary reductions eliminated 18600 positions across September through November, 1,945, as aircraft inventory completion consumed remaining material stockpiles. By December 1945, Willow Run's operational workforce contracted to 4200 personnel managing facility, decommissioning equipment preservation, and contractual obligation fulfillment. The economic implications extended beyond immediate employment statistics. Ypsilanti's population had expanded from 1,2,0,0 residents in 1940 to 4,3,0,0 by 1944. Demographic growth driven entirely by Willow Run employment opportunities. Workforce contraction triggered cascading effects. Residential vacancy rates increased from 2.1% to 34.7% within 8 months. Commercial retail revenues declined 68% between August 1945 and March 1946, and municipal tax receipts contracted 41% as property valuations adjusted to reduced economic activity. The physical infrastructure transitioned into industrial limbo, a massive production facility engineered for singular purpose, confronting operational obsolescence. The assembly line's specialized configuration precluded easy conversion to alternative manufacturing applications. Precision jigs designed for B-24 component positioning possessed zero utility for automotive production or civilian aircraft manufacturing. The clear-span architecture, revolutionary for continuous flow bomber assembly, created spatial configurations inefficient for conventional manufacturing workflows, requiring departmentalized production zones. Kaiser Frazer Corporation acquired facility operational rights in 1945, attempting automotive manufacturing conversion within bomber production infrastructure. The venture encountered systematic incompatibilities. Automotive assembly required different material flow patterns, alternative tooling configurations, and distinct quality control methodologies. Production volumes proved economically unsustainable. The facility's operational overhead demanded throughput volumes exceeding realistic automotive market demand. Kaiser Frazer abandoned operations in 1953, leaving Willow Run functionally vacant. General Motors subsequently acquired the facility in 1953, implementing comprehensive infrastructure reconfiguration for automatic transmission manufacturing. This conversion required extensive architectural modification, installation of interior support structures, subdividing clear-span spaces, reconfiguration of material handling systems, and complete replacement of specialized bomber assembly tooling. The transformation effectively erased Willow Run's original production architecture, preserving only the external structural envelope while eliminating internal systems that had generated unprecedented manufacturing velocity. Yet the facility's historical significance transcended its physical persistence. Willow Run demonstrated that industrial democracy possessed latent production capacities exceeding totalitarian military economies when mobilized through systematic organization. The assembly line validated theoretical propositions regarding mass production scalability, proving that aeronautical manufacturing complexity could be subordinated to industrial standardization protocols. The bombers continued operational service decades beyond Willow Run's closure. Final B-24 retirement occurred in 1968, when Indian Air Force decommissioned its last Liberator reconnaissance variants. Willow Run's legacy transcends the immediate metric of 8685, manufactured aircraft, encoding broader systemic insights regarding industrial democracy's latent organizational capacities when confronted with existential imperatives. The facility demonstrated that production methodology itself constitutes a strategic weapon that systematized manufacturing processes, when optimized through rigorous analytical frameworks, generate military advantages independent of technological superiority in individual weapons systems. The conceptual transformation proved more significant than material output. Pre-war industrial doctrine treated complex manufacturing as inherently resistant to mass production protocols, a domain requiring artisanal expertise and customized fabrication methodologies. Willow Run invalidated this assumption through empirical demonstration, proving that systematic decomposition of complex assembly into standardized discrete operations permitted radical throughput escalation while maintaining quality specifications. This methodological revolution generated cascading implications across post-war industrial architecture. The precision jig systems, statistical process control frameworks, and continuous flow assembly protocols pioneered at Willow Run migrated into civilian manufacturing sectors. Commercial aviation adopted these standardization principles, enabling Boeing 707 production costs to decrease 67% between initial 1,958 deliveries and mature 1,970 seconds manufacturing. Automotive industries integrated quality verification checkpoints throughout production sequences, rather than relying on terminal inspection, reducing warranty claims by 43% industry-wide between 1,950 and 1950. Beyond technical methodologies, Willow Run embodied democratic industrialism's fundamental proposition that decentralized civilian populations, when coordinated through rational organizational frameworks, generate productive capacities exceeding centralized authoritarian economies. The workers fabricating bombers weren't professional armaments manufacturers or militarized labor brigades, but ordinary citizens temporarily redirected towards strategic production, then seamlessly reintegrated into peacetime civilian economies. The assembly line's rhythm, 2.8 feet per minute, 63-minute production intervals, 22.8 aircraft daily, constituted more than manufacturing statistics. These metrics encoded the mathematical architecture through which industrial democracy proved its systemic superiority, transforming productive capacity itself into the decisive strategic advantage that rendered tactical contingencies increasingly irrelevant against overwhelming quantitative asymmetries. The arsenal of democracy, a rhetorical construct articulated in Franklin Roosevelt's December 1940 fireside address, achieved material manifestation through facilities like Willow Run, transforming aspirational political rhetoric into quantifiable industrial output. The phrase transcended propaganda, encoding an operational hypothesis that democratic industrial systems, when mobilized through systematic coordination, generate production velocities exceeding authoritarian command economies despite apparent organizational inefficiencies inherent in decentralized governance structures. Willow Run's 63-minute production interval represented the empirical validation of this hypothesis, a temporal metric demonstrating that voluntary civilian labor, coordinated through rational manufacturing protocols, rather than coercive state mandates, achieved throughput superiority across sustained operational durations. The assembly line's mechanical rhythm persists beyond its 1,945 operational cessation. Contemporary manufacturing ecosystems, lean production methodologies, just-in-time, inventory systems, Six Sigma quality frameworks inherit conceptual DNA directly traceable to Willow Run's systematic process optimization. Modern Boeing 737 production achieves 52 aircraft monthly through assembly protocols, refined from wartime bomber manufacturing principles. Tesla's automotive factories target 5,000 unit weekly production through continuous flow architectures, conceptually identical to Ford's 1,944 innovations. Yet Willow Run's ultimate legacy resides not in manufacturing techniques, but in demonstrated possibility, proof that industrial capacity systematically organized and sustained across sufficient duration transforms abstract national potential into concrete strategic dominance. The facility validated that wars are won not exclusively through battlefield tactics or technological superiority, but through the unglamorous mathematics of production, logistics, supply chain coordination, and relentless quantitative accumulation. The bombers emerging from Michigan skies between 1942 and 1945 carried more than explosive ordnance. They transported the encoded message that free societies, when confronted with existential threats, possess latent organizational capacities capable of outproducing, outbuilding, and ultimately outlasting any alternative system. Arrangement: Willow Run 8685 B-24 Liberators. 1 every 63 minutes. Victory through industrial inevitability.